Observing Derived State. At an abstract level, the data flow systems discussed in the last section give you a process for creating derived datasets such as search indexes, materialized views, and predictive models and keeping them up to date. Let's call that process the write path. Whenever some piece of information is written to the system, it may go through multiple stages of batch and stream processing, and eventually every derived dataset is updated to incorporate the data that was written. Figure 12-1 shows an example of updating a search index. Figure 12-1. In a search index, writes document updates meet reads queries. But why do you create the derived dataset in the first place? Most likely because you want to query it again at a later time. This is the read path. When serving a user Roman 3. Less facetiously, the set of distinct search queries with non-empty search results is finite, assuming a finite corpus. However, it would be exponential in the number of terms in the corpus, which is still pretty bad news. Request you read from the derived dataset, perhaps perform some more processing on the results, and construct the response to the user. Taken together, the write path and the read path encompass the whole journey of the data, from the point where it is collected to the point where it is consumed, probably by another human. The write path is the portion of the journey that is pre-computed, i.e. that is done eagerly as soon as the data comes in, regardless of whether anyone has asked to see it. The read path is the portion of the journey that only happens when someone asks for it. If you are familiar with functional programming languages, you might notice that the write path is similar to eager evaluation, and the read path is similar to lazy evaluation. The derived dataset is the place where the write path and the read path meet, as illustrated in Figure 12-1. It represents a trade-off between the amount of work that needs to be done at write time and the amount that needs to be done at read time. A full-text search index is a good example. The write path updates the index, and the read path searches the index for keywords. Both reads and writes need to do some work. Writes need to update the index entries for all terms that appear in the document. Reads need to search for each of the words in the query, and apply Boolean logic to find documents that contain all of the words in the query and operator, or any synonym of each of the words and or operator. If you didn't have an index, a search query would have to scan over all documents like grep, which would get very expensive if you had a large number of documents. No index means less work on the write path, no index to update, but a lot more work on the read path. On the other hand, you could imagine pre-computing the search results for all possible queries. In that case, you would have less work to do on the read path. No Boolean logic, just find the results for your query and return them. However, the write path would be a lot more expensive. The set of possible search queries that could be asked is infinite, and thus pre-computing all possible search results would require infinite time and storage space. That wouldn't work so well. Roman 3. Another option would be to pre-compute the search results for only a fixed set of the most common queries, so that they can be served quickly without having to go to the index. The uncommon queries can still be served from the index. This would generally be called a cache of common queries, although we could also call it a materialized view, as it would need to be updated when new documents appear that should be included in the results of one of the common queries. From this example we can see that an index is not the only possible boundary between the write path and the read path. Caching of common search results is possible, and grep-like scanning without the index is also possible on a small number of documents. Viewed like this, the role of caches, indexes, and materialized views is simple. They shift the boundary between the read path and the write path. They allow us to do more work on the write path by pre-computing results in order to save effort on the read path. Shifting the boundary between work done on the write path and the read path was in fact the topic of the Twitter example at the beginning of this book, in describing load on page 11. In that example, we also saw how the boundary between write path and read path might be drawn differently for celebrities compared to ordinary users. After 500 pages we have come full circle. I find the idea of a boundary between write and read paths interesting, because we can discuss shifting that boundary and explore what that shift means in practical terms. Let's look at the idea in a different context. The huge popularity of web applications in the last 2 decades has led us to certain assumptions about application development that are easy to take for granted. In particular, the client/server model, in which clients are largely stateless and servers have the authority over data, is so common that we almost forget that anything else exists. However, technology keeps moving on, and I think it is important to question the status quo from time to time. Traditionally, Web browsers have been stateless clients that can only do useful things. When you have an internet connection, just about the only thing you could do offline was to scroll up and down in a page that you had previously loaded while online. However, recent single-page JavaScript web apps have gained a lot of stateful capabilities, including client-side user interface interaction and persistent local storage in the web browser. Mobile apps can similarly store a lot of state on the device and don't require a round trip to the server for most user interactions. These changing capabilities have led to a renewed interest in offline-first applications that do as much as possible using a local database on the same device without requiring an internet connection, and sync with remote servers in the background when a network connection is available. Since mobile devices often have slow and unreliable cellular internet connections, it's a big advantage for users if their user interface does not have to wait for synchronous network requests, and if apps mostly work offline. See clients with offline operation on page 170. When we move away from the assumption of stateless clients talking to a central database and towards state that is maintained on end-user devices, a world of new opportunities opens up. In particular, we can think of the on-device state as a cache of state on the server. The pixels on the screen are a materialized view onto model objects in the client app. The model objects are a local replica of state in a remote data center. In a typical web page, if you load the page in a web browser and the data subsequently changes on the server, the browser does not find out about the change until you reload the page. The browser only reads the data at one point in time. Assuming that it is static, it does not subscribe to updates from the server. Thus, the state on the device is a stale cache that is not updated unless you explicitly poll for changes. HTTP-based feed subscription protocols like RSS are really just a basic form of polling. More recent protocols have moved beyond the basic request/response pattern of HTTP. Server-sent events, the event source API, and WebSockets provide communication channels by which a web browser can keep an open TCP connection to a server, and the server can actively push messages to the browser as long as it remains connected. This provides an opportunity for the server to actively inform the end-user client about any changes to the state it has stored locally, reducing the staleness of the client-side state. In terms of our model of write path and read path, actively pushing state changes all the way to client devices means extending the write path all the way to the end user. When a client is first initialized, it would still need to use a read path to get its initial state, but thereafter it could rely on a stream of state changes sent by the server. The ideas we discussed around stream processing and messaging are not restricted to running only in a data center. We can take the ideas further and extend them all the way to end-user devices. The devices will be offline some of the time and unable to receive any notifications of state changes from the server during that time. But we already solved that problem. In Consumer Offsets on page 449, we discussed how a consumer of a log-based message broker can reconnect after failing or becoming disconnected, and ensure that it doesn't miss any messages that arrived while it was disconnected. The same technique works for individual users, where each device is a small subscriber to a small stream of events. Recent tools for developing stateful clients and user interfaces, such as the Elm language and Facebook's toolchain of React, Flux, and Redux, already manage internal client-side state by subscribing to a stream of events representing user input or responses from a server, structured similarly to event sourcing. See event sourcing on page 457. It would be very natural to extend this programming model to also allow a server to push state change events into this client-side event pipeline. Thus, state changes could flow through an end-to-end write path, from the interaction on one device that triggers a state change, via event logs and through several derived data systems and stream processors, all the way to the user interface of a person observing the state on another device. These state changes could be propagated with fairly low delay, say, under 1 second end-to-end. Some applications, such as instant messaging and online games, already have such a real-time architecture in the sense of interactions with low delay, not in the sense of response time guarantees on page 298. But why don't we build all applications this way? The challenge is that the assumption of stateless clients and request/response interactions is very deeply ingrained in our databases, libraries, frameworks, and protocols. Many data stores support read and write operations, where a request returns one response, but much fewer provide an ability to subscribe to changes, i.e. a request that returns a stream of responses over time. See API support for change streams on page 456. In order to extend the write path all the way to the end user, we would need to fundamentally rethink the way we build many of these systems, moving away from request/response interaction and toward publish/subscribe data flow. I think that the advantages of more responsive user interfaces and better offline support would make it worth the effort. If you are designing data systems, I hope that you will keep in mind the option of subscribing to changes, not just querying the current state. We discussed that when a stream processor writes derived data to a store database, cache, or index, and when user requests query that store, the store acts as the boundary between the write path and the read path. The store allows random access read queries to the data that would otherwise require scanning the whole event log. In many cases, the data storage is separate from the streaming system. But recall that stream processors also need to maintain state to perform aggregations and joins. See stream joins on page 472. This state is normally hidden inside the stream processor, but some frameworks allow it to also be queried by outside clients, turning the stream processor itself into a kind of simple database. I would like to take that idea further. As discussed so far, the writes to the store go through an event log, while reads are transient network requests that go directly to the nodes that store the data being queried. This is a reasonable design, but not the only possible one. It is also possible to represent read requests as streams of events, and send both the read events and the write events through a stream processor. The processor responds to read events by emitting the result of the read to an output stream. When both the writes and the reads are represented as events and routed to the same stream operator in order to be handled, we are in fact performing a streamed table join between the stream of read queries and the database. The read event needs to be sent to the database partition holding the data. See request routing on page 214. Just like batch and stream processors need to copartition inputs on the same key when joining. See reduce I joins and grouping on page 403. This correspondence between serving requests and performing joins is quite fundamental. A one-off read request just passes the request through the join operator and then immediately forgets it. A subscribe request is a persistent join with past and future events on the other side of the join. Recording a log of read events potentially also has benefits with regard to tracking causal dependencies and data provenance across a system. It would allow you to reconstruct what the user saw before they made a particular decision. For example, in an online shop, it is likely that the predicted shipping date and the inventory status shown to a customer affect whether they choose to buy an item. To analyze this connection, you need to record the result of the user's query of the shipping and inventory status. Writing read events to durable storage thus enables better tracking of causal dependency. See ordering events to capture causality on page 493, but it incurs additional storage and I/O cost. Optimizing such systems to reduce the overhead is still an open research problem, but if you already log read requests for operational purposes as a side effect of request processing, it is not such a great change to make the log the source of the requests instead. For queries that only touch a single partition, the effort of sending queries through a stream and collecting a stream of responses is perhaps overkill. However, this idea opens the possibility of distributed execution of complex queries that need to combine data from several partitions, taking advantage of the infrastructure for message routing, partitioning, and joining that is already provided by stream processors. Storm's distributed RPC feature supports this usage pattern. See message passing and RPC on page 468. For example, it has been used to compute the number of people who have seen a URL on Twitter, i.e. the union of the follower sets of everyone who has tweeted that URL. As the set of Twitter users is partitioned, this computation requires combining results from many partitions. Another example of this pattern occurs in fraud prevention. In order to assess the risk of whether a particular purchase event is fraudulent, you can examine the reputation scores of the user's IP address, email address, billing address, shipping address, and so on. Each of these reputation databases is itself partitioned, and so collecting the scores for a particular purchase event requires a sequence of joins with differently partitioned datasets. The internal query execution graphs of MPP databases have similar characteristics. See comparing Hadoop to distributed databases on page 414. If you need to perform this kind of multi-partition join, it is probably simpler to use a database that provides this feature than to implement it using a stream processor. However, treating queries as streams provides an option for implementing large-scale applications that run against the limits of conventional off-the-shelf solutions.